Welcome to Go Lesson 30. Today we will learn how to write benchmarks and profile our Go code for performance. We will cover benchmark functions, memory stats, table-driven benchmarks, and CPU profiling. Go's testing package includes powerful benchmarking tools built right in. Let us start with the basics of benchmarking in Go. First, we create functions to benchmark. Here is a recursive Fibonacci function. Recursive Fibonacci has exponential time complexity, which makes it perfect for benchmarking. We also add an iterative version using a loop, which is much faster. Let us review the source code. Now for the benchmark file. Benchmark functions start with benchmark and take a pointer to testing.B. We first write a unit test to verify correctness before benchmarking. Benchmark fib10 uses for range bn, the classic benchmark loop pattern. Benchmark fib20 benchmarks a larger input. Notice the time difference. Benchmark fib20 loop uses b.Loop, a modern Go 1.24 feature that prevents compiler optimizations from skewing results. Let us review the benchmark file. Watch the output. The -8 suffix shows the number of CPU cores. The ns/op column shows nanoseconds per operation. You can run a specific benchmark by name with the -bench flag. The -count flag runs benchmarks multiple times for more stable results. Now let us compare different implementations using benchmarks with memory statistics. We create 3 ways to concatenate strings. First, the plus operator. The plus operator creates a new string each time, which is slow for many concatenations. Sprintf is even slower because of reflection and formatting overhead. Strings.Builder is the most efficient. It uses a byte buffer internally. Let us review the three approaches. Now for the benchmarks. Notice the setup code before b.Loop is excluded from the timing. Each benchmark creates a slice of 100 strings, then measures concatenation speed. Let us review the benchmark file. Watch the benchmem output. b/op shows bytes allocated per operation. allocs/op shows the number of allocations. Table-driven benchmarks let you test across different input sizes. We create two search algorithms. Linear search scans every element in order. Linear search is on-, it gets slower as the input grows. Binary search uses sort.search_ints for O-log-n, performance on sorted data. Let us review the search functions. Now for the table-driven benchmarks. We use b.Run, just like t.Run from unit tests. We define sizes from 100 to 100,000 elements to see how each algorithm scales. Each sub-benchmark gets its own name, like benchmark linear search /10,000. Let us review the benchmark file. Watch how linear search time grows linearly, while binary search stays nearly constant. You can filter benchmarks by name. Here we run only the linear search benchmarks. You can also filter by sub-benchmark name. /10,000 runs only the 10,000 element benchmarks. CPU profiling helps you find performance bottlenecks in your code. We create text processing functions. Word frequency splits text and counts words. It uses strings.Fields to lower and trim. Each is a potential bottleneck. Top words finds the most frequent words by sorting the frequency map. Let us review the source code. Now for the benchmark file. We create a large sample text for realistic profiling. The tests verify our functions work correctly before profiling. The sample text variable repeats a paragraph 100 times for a meaningful workload. The benchmarks use b.Loop to measure performance. Let us review the benchmark file. The CPU profile flag generates a cpuprofile file during benchmarking. Go tool pprof opens the interactive profiler. The top command shows where time is spent. The flat column shows time in each function. The cum column shows cumulative time including calls. Let us recap benchmarks and profiling in Go. Benchmark functions start with benchmark and use b.N or b.Loop for the test loop. The benchmem flag shows memory allocations per operation. Table-driven benchmarks with b.Run let you compare across input sizes. CPU profiling with cpuprofile and Go tool pprof reveals performance bottlenecks. Thanks for watching. In the next lesson, we will explore the HTTP client in Go.